Hi guys, very good afternoon to every one of you. This is your chemistry expert Sanjay Arya sir, and today we will be dealing with one of the very important concept from organic chemistry that we generally skip because it's difficult to learn and it has lots of things to rote learn about. Those students who are preparing for NEET, this chapter is basically repeated in English in your chemistry as well as in biology. So you study the same chapter twice and that's why it's easier to them. Coming to our JEE aspirants, this chapter is a hurdle and we have to basically cross this hurdle anyhow. So that's why I've come up with this chapter. I made the notes by my own. So guys, the notes are pretty much self-explanatory. Download the notes, join our Telegram channel where you can basically go through the whole notes and can find out any difficulty and just ask me over in the comment section of the same session ongoing. Before starting guys, let me give you an idea that if you want to enroll with us or if you want to study over here on the Unacademy application with all your top educators from India, you have 3 special courses just available for 4499. Just for the price of 4499, you can avail any of the course. If you are in 11th standard, 1 year course is called as Nimbus. For 12th, it is called as Nexus 1 year, and for Phoenix batch, it is for Dropper. And not just a particular set of faculties you can get. You can basically enroll with any of the ongoing or teaching educator over there on the application, right? So yeah, that's it. Okay, and if you want to avail this thing, you want to avail this offer, don't forget to apply the code CSA sir. Apply code CSA sir. Okay, so this code will give you this offer availing every batch for 4499. Now let me take you to the definition of this chapter. Name is carbohydrate. The very first topic that comes is carbohydrate. Before that, let us understand the name of this chapter, named as biomolecule. Okay, so biomolecule, as the name itself suggesting. Sir, your Unacademy profile is showing you left Unacademy. No, I'm it might be showing actually. So many things are right now going on, but it will be resolved very soon. And thank you for your concern, Mr. Protriactive. Okay, chalo, let's come back to the topic. Biochemistry is the branch of chemistry or the science that helps with the what kind of composition of chemicals goes in and out of our human living life is called as the biochemistry, the study of that part of the science. Now coming to biomolecule, these are some set of chemical molecules which are basically required for working of our body or working of the biological processes of our all living organisms. Okay, this is what we call as the biomolecules. Now these biomolecules can be further classified into 2 categories. One of them is organic, another one is inorganic. So bioorganic and bioinorganic. You might have heard about so many minerals we require for our body, so many cations, anions we need. We sometimes need some electrolyte in our body, keep our blood flow and moving everything very smooth. That also require with some of the inorganic metals and their metallic complexes or some salts. This kind of molecular composition comes under the category of bioinorganic. Now coming to the organic part, our body itself composed of so many things, just like carbohydrates, fats, lipids, enzymes, and even protein, vitamin. These all categories are coming under bioorganic biomolecules, which are organic in nature. So these are some important organic chemicals, which are carbohydrate, proteins, and nucleic acid, that we'll study one by one. This is just a classification of biomolecules. And then others are lipid, vitamin, and hormones, for which we have vitamins under our syllabus that we'll study very soon. And rest of them will be understanding one by one. So let us first start it from the carbohydrate. The very first category of biomolecule is called as carbohydrate. Now the meaning of carbohydrate is hydrates of carbon. Carbohydrate means hydrates of carbon. So this is an older definition that let's take an example, that if I say glucose. So what is the formula of glucose? We all know the formula of glucose, which is C6H12O6, which can also be written down as C6 NH2O whole 6. This is how it satisfies the older definition of, we call it carbohydrate. Anyhow, this definition is not true for all the carbohydrates, and that's why it has been discarded. And no, we are not supposed to write down anything, or even any kind of example can be explained in this way. But if you take the example such as, if I talk about acetic acid, acetic acid has a formula of C2H2 whole twice, but it is not a carbohydrate. It doesn't come under the category of carbohydrate. It's simply carboxylic acid. Okay, acetic acid is simply carboxylic acid, not any of the biomolecule. In fact, carboxylic acid doesn't come under any category of the biomolecule. It's simply an organic compound. Talking about formaldehyde also has the C1H2 formula, but still these two are simply organic compound and not just some carbohydrate. We also have some of the carbohydrate whose formula doesn't match with CXH2OY. It doesn't match with the hydrates of carbon formula, and for this the example is ramenose. The ramenose has a formula of C6H12O5. We are not justifiable by this formula. It doesn't come with CXH2OY. Also, deoxyribose, one of the sugar that we are going to study under nucleic acids. This is your C5H10O4 and do not belong to the formula of CXH2OY. That's why we call them the older definition of carbohydrate. Now, I'll tell you the modern definition that has been followed these days. This is important. So, what is the definition of carbohydrate? A carbohydrate is that particular biomolecule which contains polyhydroxy. Okay, first of all, it should be optically active. Number one point is it should be optically active. It should contain polyhydroxy groups, multiple hydroxy groups, along with an aldehydic or ketonic functional group. And this is what we call it as a carbohydrate. So, all the carbohydrate come to this category where three important things are there. The number one is aldehydic or ketonic group, number two is polyhydroxy, and number three is the chirality. That chirality is because of the presence of some chiral carbon atoms over there. Let's look at the example. We have D-glyceraldehyde, one of the example of carbohydrate. So, one hydroxyl group is there, aldehydic group is there. This is organically this is optically active also because of this chiral carbon attached with four different groups. This comes under the category of D-glyceraldehyde. We are talking about polyhydroxy. That means it should be two or more than that. Minimum number of hydroxy atoms that we have to maintain is 2. And also, in order to make this compound or this carbon optically active or as a chiral carbon, we had to use another hydroxyl group. Okay, we have D-erythrose, one of the example. Erythro means same side, thrio means opposite side. Thrio, erythro, thrio, and then D-fructose, D-glucose. Multiple examples are there. Don't worry, guys. We'll come to each and individual of the example in very detail. But just now, take an idea what is the definition of these compounds called as the, what these compounds are? Carbohydrate. Carbohydrates are nothing but the polyhydroxy aldehydic or ketonic compounds with optical activity. Okay. Now, let me take you to the next few examples and the classifications on the basis of the functional group. Polyhydroxyaldehyde, which are called as aldose. Polyhydroketone called as ketose. So, ketonic sugars are there, aldehydic sugars are there. They are respectively called as the carbohydrate under the category of their main functional group. So, main functional group could be an aldehyde or ketone. Based on that, they are named as aldose, ketose. The examples of aldose are glucose, mannose, galactose, ribose, glyceraldehyde. In fact, many of them are there which are aldose. The example of ketonic is fructose, ribulose, in fact ribose. They all come under the category of ketonic sugar or ketonic functional group containing carbohydrate. That was one classification we had. The another second classification is based on whether these compounds can be oxidized by Tollens reagent, Benedict solution, Felling solution. Can these compounds be oxidized? So, under that we have another simple definition, which is whether they are reducing or non-reducing sugars. So, reducing and non-reducing sugars is the another mode of classification. Guys, I will not disturb so much this on written these notes and all, because they are very much self-explanatory and very well neatly written over there. I don't want to disturb it. So, I'll try to write as simple as possible, as less as possible. Reducing sugars are those sugar which can be oxidized or which reduced to the tolerance reagents such as tolerance reagent, Fellings and Benedict solution. These all are called as the mild oxidizing agents. Then coming to non-reducing sugar, they do not reduce to the tolerance reagent, Fellings and Benedict solution. That's why they are coming under the category of non-reducing. So why basically they can't reduce sugar, can't reduce these reagents, and these can reduce the reagent? Because they have availability, these solutions have availability of free aldehydic or ketonic group. Now you might be wondering, sir, ketone does not give any reaction with toluene, Fellings and Benedict. Ketone do not give this test, only aldehydes give. But under basic conditions, ketones which are also having alpha hydrogens, they may undergo tautomerization, forming their enol form, and that enol form can again form another aldehydic group. So any ketonic group can be converted into aldehydic group under equilibrium under this property called as tautomerism, and due to which all what I must say, they are monosaccharides. All the monosaccharides which have their openly available aldehydic and ketonic group can undergo this particular test, and yes, they can reduce tolerance reagent, Benedict solution, Fellings solution. That's why we call them reducing sugars. So they should have at least what? They should have at least one hemiketal functional group or hemiacetal functional group, which automatically gets converted back into the aldehydic or ketonic group when comes under the basic medium of these giving reagents. Okay, all the see, this is a star, I'm marking it, that all monosaccharides and oligosaccharides except sucrose, the only oligosaccharides which do not give this test or which cannot reduce these reagents is called as, or which that does not undergo oxidation, will be the sucrose, because of it's both the ketonic and aldehydic groups are basically connected or are engaged into some chemical linkage, which is also called as glycosidic linkage. We'll come to know about that very soon. But because of that link, this ketonic or aldehydic group is not available. That makes sucrose a non-reducing sugar. Rest all the oligosaccharides and monosaccharide sugars are the reducing in nature. Now let's take an example as of now, but now once we'll be moving forward to the another classification based upon the number of this aldehydic ketonic group, then we'll basically discuss it very soon. We have another example, non-reducing sugar, and they all should have acetal linkages. What kind of linkages are we talking about? This is containing hemiacetal linkage, but this is containing what? OR and OR group. That what it makes it hemiacetal, sorry, acetal linkages or ketal linkages. An example is the all polysaccharides in which all the aldehydic and ketonic groups are linked together by this kind of link, which is your COR and OR group. And over here also, this is one of them is OH and another would be OR, but this OH and OR group is called as hemiacetal. This group is called as ketal, where ketal or acetal, depending upon the attack, was based on as aldehyde or ketone. Okay. Anyways, we have given the enough of the example, but the only non-reducing oligosaccharide is sucrose. Rest all the polysaccharides are also coming under the category of non-reducing sugar. A reason I have already explained you. Okay. Hopefully you all know about the reason. The reason is pretty simple, that they do not have available hemiacetal group which can easily be converted back into their aldehyde or ketone, and then leading to the formation of their oxidized version, reducing these given number of substances. That was one easy thing we have come across. Now I'll take you to the next thing without too much writing on the board and wasting our so formed very beautiful looking like notes. The another one is called as on the basis of sweetness. Mainly carbohydrates are sweet in nature, and that's why they are recalled as sweet. We call them sugars. We call them sugar. So the one which are sweet in taste are called as sugars. The one which are not in sweet in taste, they will be called as non-sugar. They are sugar and non-sugar. Anyways, they almost every one of them are sweet in taste, except some lower ones. Lower ones could be neutral in taste or not so good in taste, but yes, all of them are sweet in taste. Even the bigger ones are very sweet in taste. Number 4 is on the basis of the carbon atom they are containing. If the number of, see, how many would you think minimum number of carbon atom and are required for any aldose sugar? So this kind of questions comes in exam. minimum number of carbon atoms needed in needed in a needed in an aldose. If aldose sugar is there, how many number of carbon atoms must be needed? Okay, you please submit me the answer. Until then, I'm making another question, that what is the number of minimum number of the carbon atoms needed in a ketose, needed in a ketose. So one of them is aldose, another one is ketose. We got to tell them how many of them are needed. So basically the answer over here is 3, that it should be optically active with different groups. This will be CH2OH polyhydroxy. This is CHO group. So how many number of carbon atom do you need? Just count them. This is your answer, 1, 2 and 3. Now how many number of carbon atoms will be needed in a ketose sugar, a smallest sugar? Minimum number of carbon atoms have been asked. So the actual answer of this question is actually 4. How come? Because ketonic group is a central group, or we can say it's not a terminal group, it's a non-terminal group. It comes between two carbon atoms. So we have to make this thing as CH2OH. We have to make this thing as CH2OH. We have to actually make one of them as chiral, otherwise it will not be optically active. Let's say if this is chiral, so the final one will also be containing CH2OH. Now can you count this number, guys? Can we count this number? Number will be 1, 2, 3 and 4. At least 4 carbon atoms are needed. So this kind of question usually comes in your board exams also, somewhere in JEE or some lighter level of questions. Next comes another classification based on the products of hydrolysis. Products of hydrolysis means, so whenever we add water, they are first dissolved. But oligosaccharides, the one which are containing more number of carbon atoms, and polysaccharide which also are containing more than 10 carbon atoms in fact. So these polysaccharides will basically undergo dissociation in the individual monosaccharides. Okay, individual monosaccharides will be known over there on the basis of the number of individual monosaccharides which we are getting as a product. This is how they are segregated under this category of. One of them is called as monosaccharide, which does not undergo hydrolysis. It can be dissolved in water, can form a uniform solution. Sugars are generally dissolved or soluble in water, but they do not undergo hydrolysis. They will not give you any further product upon hydrolysis because they are made up of only just one molecule. Now let me take you to oligosaccharide. Name itself suggests oligo, might not be suggesting anything. Oligo is, what is oligo? But oligo means 2 to 10 units it can give you, up to 10 maximum and minimum of 2. So like 2 monosaccharide units were present over there. They were linked through a particular specific type of bond called as glycosidic linkage. We'll come to know about that also. And any particular saccharide which is having up to 10 units as monomer, they all come under the category of oligosaccharide. If it is more than that, then we call it polysaccharide. Look at the examples of polysaccharide. They give more than 10 units, okay? Glycogen and cellulose, starch. These are some very popular examples of these category of carbohydrate. I hope this part is absolutely clear to all of you. Yeah. So now taking you to the classification, mono, oligo and poly. We'll talk about each and individual of them in very detail, because if I talk about all the type of the biomolecules that we are going to cover in this chapter, the most important is carbohydrate. Carbohydrate has a depth of its diversity and also in its classification, and that's why so many questions repeatedly have been asked in your JEE Mains and Advanced examination these days. However, amino acid proteins also have some importance these days. Some questions upon vitamins also have appeared in the exam of JEE Main specifically. So we'll come to know everything in detail, but let me reveal that carbohydrate will take the maximum of the time. We have the first thing, that is monosaccharides. Some of the examples have been mentioned: glucose, fructose, galactose. Oligosaccharides also, some of the example is sucrose, lactose, maltose. Polysaccharides are starch, cellulose, glycogen. And a typical polysaccharide undergo hydrolysis and requires N-1 H2 molecule, because basically these number of they will be added by N number of monomer will require N-1 water molecule, because they are like when they actually were made. Like, let's look at this. This monosaccharide was connected when one H2O unit was eliminated out, right? So this is how this was formed. This is the glycosidic linkage. Similarly, this, let's say MM is over there and we are adding one more M over there, then one more water molecule will be removed there, and then it will be forming MMM. So that's what I'm saying, that if I go up to the nth level, and let us say if I make this one more H2 molecule will be going there, and it becomes MM, N, like that. Okay, N units are connected over there. Then this is how it is formed. We can also call it like N times of M. So how many molecules have been eliminated out? So out of 2, it started from the elimination of 1, then from 3 to 2, and going like that. That in total, how many molecules basically have been eliminated out of there? Eliminated. If we add all of them together, right? If I say, if I am adding all of them, then this is how it looks like, that N times of M, when eliminated out with N-1 number of water molecules, they formed M, like that, N times, or this can also be written down as M, N polymer. So try to understand that for a disaccharide, one water molecule might have been eliminated out. For a tetrasaccharide, 3 number of water molecules have been eliminated out. That's how we predict the number of water molecules eliminated out. So that's a general formula for a polysaccharide. Now we can apply this formula for disaccharide, trisaccharide, tetrasaccharide, any one of them. Which one is not a carbohydrate? A carbohydrate is pretty simple, that it must contain polyhydroxy or aldehydic or ketonic group, which a lactic acid does not contain. Lactic acid is the correct answer. We also took this example in explaining that its formula is belonging to that CnH2O whole N, but it is not a carbohydrate. Ribose sugar is what? So ribose sugar, will come to it. It's a ketopentose, deoxyribose sugar. I think it's a ketopentose. No, aldopentose. Sorry, my bad. Not ketonic sugar. That is an aldehydic. Now you might be wondering, like, how ribose sugar, we haven't studied about ribose sugar, how did it come? So guys, don't worry, we will be learning a whole segment called as nucleic acid. So there we study 2 type of sugars about there. One of them is called as RNA, one is called as DNA. RNA is called as ribose nucleic acid, and DNA is called as deoxyribose nucleic acid. There we use a carbohydrate, a monosaccharide we use over there, which is a aldopentose, and that is one of the example. So we will be coming to that, and then we will be understanding this concept in very much detail. Unless then we will come to the monosaccharide and we will learn about monosaccharide in very much detail. So we have this formula. General formula will definitely be a CXH2OY, where X can move up to 3 to 8, and it may or may not follow, because as I told you that some of the examples like where Ramenos was not following this formula. Okay, this is not a very specific formula that everyone has to follow. No, not like that. It's a general formula that we can write for all the monosaccharide. Now, these monosaccharide are these much number of examples. Some of them we must know in a much detail. So let us come to first examination of the stereochemistry of glucose. This was done by Fischer, and there where he came up with the proposal of the Fischer structures. So that's how the Fischer structure of glucose look like. There is a one aldehyde group is there. So 1, 2, 3, 4, 5, 6 number of carbon atoms are there. You must know about their classification also, because the structure that you are right now seeing is called as D. This is called as D glucose, where capital D is actually its relative configuration. I'll explain you what does it mean. D is the relative configuration. Positive is called as its optical activity, or also called as the absolute configuration. So basically it reveals us that in which direction the optical activity will be shown. Positive means it will rotate the plane polarized light under into the clockwise direction when it is passed through the solution of glucose, and this glucose is the molecular name itself. So we'll come to know about each and individual one by one we'll do it. So first of all, let us understand what is the meaning of capital D and capital L. I will not waste the notes. Okay, notes are pretty good. So if you want to know about glucose, that what you have to do is, I'll explain it using one example of glucose itself. So we are right now understanding the concept of capital D and capital L. This capital D means right, the capital L means left. So what we will be doing, let's say I'm having a D positive glucose, and this is the open structure glucose. So this is how CHO used to look like at the top of every carbon atom, or this backbone chain. Then on the first carbon atom we had OH group in the right hand side and H group in the left hand side. Then we have third carbon will be having in left and right, and then all will be there in right hand side. See, 1, 2, 3, 4, 5, and the final will be CH2OH. So why am I calling this thing as a D glucose? Because the last carbon atom, if you started from there, 1, 2, 3, 4, 5, 6th. So the last chiral carbon atom we are talking about. Okay, if we start from there, it will become what? Last chiral carbon. The last chiral carbon itself has a hydroxyl group on the right hand side. This is in right hand side. Now if you take a mirror image of this molecule, if I take the mirror image of this molecule, this will now become it will become L, capital L, negative glucose. Why is it so? Because sir, it's a mirror image which is a non-superimposable mirror image. So that's why this mirror image is an enantiomer of this compound. So this will be looking like, this will go in left and this will come up in right. Then we'll be having one more OH, one more OH and H, and finally we have CH2OH. So that's how it looks like. Again, you will see, you will count the number 1, 2, 3, 4, 5, 6. What do you see? The last chiral carbon is over here, and this comes to the left, right? This is what we are meaning for D and L glucose. People generally get confused. They do only change in the final. So this is not L minus glucose looks like. It comes out of from D itself. The naturally existing glucose is D positive glucose. If I take the mirror image of this compound, it becomes L minus glucose, which will be giving you exactly the opposite property of this compound towards the optical activity, towards the optically active reactions, or I must say plane polarized light like that. Hopefully this part of this chapter is absolutely clear to all of you. Now I'll take you to some example, and I would like to give you one more example that DL naming is not given to every single one of them. It is only given to those Fischer projections where all the carbon atoms are chiral, and then we have to reach to the final one from the backbone, and we have to reach to that part where OH or NH2. Let's say if there's an amino kind of compound amines are there and NH2 group is found in left hand side, it will become capital L. If it is in right hand side, it will become capital D, and similarly with the OH group. So see, this is the mirror image of the compound, as we can all see, and we have to look for this thing only that I have just explained you. Let us come to the molecular tree. What is the meaning of this molecular tree? I would like to give you the examples of all monosaccharide, disaccharide, trisaccharide one by one. Only monosaccharide with different number of carbon atoms. Initially, for the very first thing, we have D-glyceraldehyde, the simplest aldehydic or aldose sugar, D-glyceraldehyde. Why am I calling it D? Because in right hand side, so it will become D, not a problem. Then this is basically containing 3 carbon atom, then we'll take it to 4 carbon atom, 3 to 4. Okay, this is the meaning of the sugar molecular tree. From D-threose, we saw it over there, basically glyceraldehyde. We are calling it erythro and threose. How did we call it erythro and threose? The name of erythro means same side. The main of this erythro means same side. This name means opposite side. But again, I have to make it what? Capital D. So the last chiral carbon atom over here must contain the OH group in right hand side. If it is in right hand side, this will become D component of this threo. And then if I get this OH group in the opposite side of this, it will become D-threose. This is called as D-erythros because these OH groups are in the same side and these are right now in opposite side. As you all can see, these are in opposite side, these are in same side. Now let me not waste this diagram. It's a very important diagram and I have made it by very difficult processes. So that's why I want to keep my notes very neat and clean that you all can understand. Now coming to tetrose. So till threose we have just covered it. Tetrose will be containing 4 carbon atoms. So one of the example was D-threose. We just have understood this D-threose coming over here, D-threose. Erythro. We had D-erythros. That erythro can also further be containing 5 number of carbon atom and becomes what? Ribose and arabinose. How we are calling them ribose and arabinose? So basically we can say they are C2 anomer, C2 epimers. Anyways, what is this epimer that we also understand, but right now take an example. Let me write it that if we compare these two, ribose and arabinose, what are they to each other? We'll call it, see, this is 1 and 2. Only the position is changed on second carbon atom. D cannot be changed. Erythro means 2 should be in the same side, and the one which is not in the same side, which is opposite in the side, it has become C2 epimer. C2 epimers. Then hexose, we also have plenty of the terms over there. So basically hexose means 6 carbon atoms are there. So one in which all these are in right hand side, all these are in right hand side. This is allose, D-allose, then it becomes D-altrose. These two are C2 epimer, as you all can see. Then we have D-glucose, where the third carbon atom is having an opposite direction. All of them are the same one. And we also have called as mannose, where fourth carbon atom, see 1, 2, 3, 4. 4 carbon atom is, no, not fourth. I think this is a C, glucose and mannose were C2. 1, 2 has opposite only. 3 same. So guys, this is actually C2 epimer of each other. But anyways, this is something which we call it anomer, where we call epimer. This is something that we'll understand very soon, and it's an important concept. Okay. So till now, what I've done is I have given you all possible these monosaccharides along with their explanation why they have been named after erythro, threo, same side, opposite side, like this ribose, arabinose, allose, pelose, all. Then if I take the example of threo, from tetrose, if I take the example of threo, it's further be classified into 2 categories. One of them is 2 are having in opposite direction like these two, and then one which is having in right hand direction is called as xylose, and the one which is containing in the left hand direction is called as D-lexose. D-lexose. Why am I calling it D? Because the last carbon atom with chirality is in right hand direction. Then comes the hexose. This has become glose, exactly like the same. These are two opposites, and then they are moving in the same direction. Glucose. Then it is like idose, D-idose. D is because of this. Idose is why is it isose? Because the third carbon atom is having this is like C3 carbon. C3 epimers are there. These two of each other, glose and idose. Galactose, which is actually having the fourth carbon atom in the opposite side. If we compare it from that one, and then comes the talose, which is having at least a few more changes that are possible, that is talose. Anyways, we are not supposed to total down every one of them, but just take an idea that what I have come across with it. Glucose has a C2 epimer called as mannose, and glucose also has a C4 epimer called as galactose. These two are important. Rest will come to one of them individually and then we'll understand. Question is, natural glucose is termed D-glucose. Why is it so? Because the OH on the second carbon is on the right hand side, which is false. Because OH on the sixth carbon, no, sixth not, fifth chiral carbon should be one. Fifth carbon, this is true. Why? Because it should be what? It should be the last chiral carbon. If we start it from the most oxidized group, if you want to name it according to the IUPAC, your last carbon atom of the backbone chain will be fifth only, which is chiral, last chiral carbon. It is dextrorotatory, then it will become, it is positive, which is representing the dextrorotatory nature. Again, it is false statement. False on the behalf of what has been asked. Next is corresponding configurations of for 4 aldose. Aldose means aldehydic sugar, and they all are tetrose actually. If you see them 1, 2, 3, 4, they all are belonging to the category of tetrose. So we have to give the answer whether they are D or L. Look at this. Look at this. Last chiral carbon. Last chiral carbon. Last chiral carbon and last chiral carbon. We have to start it, but from most oxidized group. 1, 2, 3. So what do you call it? Right hand side D, right hand side D, left hand side L, L, DDLL. Where can you find DDLG? DDLL. D is the correct answer. That's how we name it. Going forward with the epimer, a topic that I was earlier discussing with you, that one of the very important topic. Epimers means two structures are exactly same in the number, will be same in the molecular formula, will be same in everything. Just one chiral carbon will be having different positions of the group, opposite positions of the group. These two are called as the epimer to each other. In fact, these two can also be called as, these two epimers will always be diastereomer. Diastereomers to each other. So let us take an example, and we are actually if we take about the we call it like if we take only 3 carbon atoms over there, in these 3 carbon atoms they will be an enantiomer to each other, and these two are not called as the epimer, they are simply enantiomers to each other. But epimer means they are the diastereomers of each other, because what's happening here, not the whole composition, they are not mirror images of each other, they are not non-superimposable mirror images. Instead, they are simply one of the chiral atom is having different configuration, that we can see this one and this one. So which carbon atom you might have seen this thing, 1, 2, 3, 4, 1, 2, 3, 4. We have seen it on second carbon atom, it has been changed. These two are C2 epimers of each other. That's what I can explain you as of now. This is how we have to name them, C2 epimers of each other. We would also have taken the triose where 3 carbon atom would have been there. We call it diglyceraldehyde. The diglyceraldehyde and L-glyceraldehyde are actually enantiomers to each other. They are non-superimposable mirror images of each other. But now talking about them, these images are also non-superimposable, but they are not the mirror images. These kind of compounds are called as diastereomer of each other. So these with a number of 4 carbon atoms will be having a C2 epimer. This C2 epimer is a diastereomer of each and another. So let me call this compound as D-erythrosine, let me call it D3Os. They too are what I can call it diastereomers of each other and C2 epimers of each other. So we have plenty of such examples where as per the sugar tree we can see that ribose, arabinose, allose, altrose, and these were in the couple ribose and arabinose were the epimers of each other, allose and altrose of the C2 epimer of each other. Xylose and lyxose were also are the epimers of each other. So that's how we name the epimers. So these are some important, let me write it, what I am right now teaching is an important epimers of glucose. I am right now teaching you the epimers of glucose. So you all know about the structure of glucose. You also know that if we change the position of OH and H under some of these specific number of carbon atoms, such as on second one or the fourth one, the second one is called as mannose, and the fourth one that has been changed with the glucose taking as a primary structure. If we change the configuration of OH and H and shift it oppositely to the glucose, it becomes galactose. So they are C4 epimers of each other. Okay, that's how we explain it. So that's it. Now we'll come to the determination of the glucose structure. We have just finished properly the classification and about the monosaccharides and all. Now one of the very important monosaccharide is glucose, another one is fructose. So glucose and fructose we have to study in detail one by one. So how the experiments were undergoing, how did we come to this conclusion that it has a linear structure, 6 carbon atoms are there, or what else is there? That is what we have to understand in this particular segment, determination of glucose structure. So glucose has a molecular formula of C6H12O6. That is how we have got it, because we all know that this has a formula of C6H2O6. We can easily determine the percentage of carbon atom in it, and then we can find out the empirical formula suggested as this one. That's how we come to know about the complete molecular formula. Because see guys, what happens is there are some very sensitive machines that gives us the exact chemical composition present inside a substance. So how much of the percentage of carbon is there, oxygen is there, everything that you can identify from some sample of the glucose. So 1 gram of sample of this glucose contains this much number of percentage of carbon, this much percentage of hydrogen and oxygen, and we try to identify its formula. It's basically empirical formula which might have appeared as C1H2O1. Then C1H2O1, by estimating its molar mass, became the formula C6H12O6. So this is the molecular formula of C6H12O6 that we have depicted from the empirical formula. Number 2 is how many number of carbon atoms are there, how to determine that part. So we are reacting with the HI and heating it. HI, which behaves as a reducing agent, this might be working as a reducing agent. This reduces the whole oxidized group under this carbon compound or alkane and forms as a N-hexane. Since because it is containing 6 number of carbon atoms, these all carbon atoms are connected in a straight chain. That is also given by this outcome. Then we have determination of glucose structure. We made it to be reacted with ammonium hydroxylamine. We call it hydroxylamine. So there are 2 things. One of them is hydroxylamine. I don't want to spoil this perfectly written notes. So I am writing very small, very lessly, so that you can understand what I am trying to explain you. Hydroxylamine, and this is called as hydrocyanic acid or hydrogen cyanide. These reactions have been covered under a chapter called as amines, not amines here. This reaction has been taken under aldehyde and ketones, chemical reactions. These reactions comes under. So anyways, it's a very easy reaction that CHO group will actually participate and on the reaction with the NH2 OH, this water will be eliminated out. This is how the H2 group will be eliminated out, and so formed oximes are formed. Oxime. If it is formed with aldehyde, it is called as aldoxime. It is with ketone, it becomes ketoxime. Then we have cyanide here, where CN goes attack there, and this has become OH and this has become CN like that. This is called as cyanohydrin. Cyanohydrin and oximes are the product. Okay. So what does it basically signify? Why are we conducting this experimentation? So this kind of reaction are called as nucleophilic addition reaction. These are the example of nucleophilic addition reaction. And these nucleophilic addition reactions are actually representing or showing you the presence of an carbonyl group, aldehyde or ketone. Next is determination of the glucose structure is going on, and then we are right now trying to figure out that how many ketones are there, how many number of ketones and aldehyde groups are there. So we made it to be reacted with bromine water, which is working as a mild oxidizing agent. This mild oxidizing agent oxidizes only to the CHO, forming COH group. This is called as gluconic acid. Learn the name. There is one gluconic acid, one of them is called as glucaric acid. Glucaric acid has two COH group at the first and sixth carbon atom, or like COH group containing the carbon atoms of first and sixth of this chain. Then if we make it attacked by the concentrated HNO3, then it has converted 1 degree. This is your 1 degree alcoholic group is there, and we also have an aldehyde group over here. This has been converted into COH, this has been converted to COH, 6-member carbon atom. This is called as saccharic acid. We also called it as saccharic acid, and earlier it was also called as glucaric acid. So there is a difference between gluconic has only one COH group, glucaric has a couple of like COH group over there. This is the difference. This proves the presence of primary alcohol. This reaction is proving this. This might ask in the exam that presence of this, presence of that proves what in the structure of glucose. So what is it proving? It is also proving that there is a one primary carbon atom over there. Now what about the all 2 degree carbon, basically 2 degree hydroxyl groups over there? One of them is 1 degree alcohol, one of them is aldehyde. What about the rest 4? For this rest 4, we will make it to be attacked by AC2, called as the acetic anhydride. What we call it? Acetic anhydride. The structure of acetic anhydride, AC2O, is like this. CH3. This is called as acetic anhydride. So basically, whenever any alcoholic group is there, let's say this is ROH is over here. So guys, you all know this is RO negative, H positive, and this O negative group goes over there, and this group departs, so that this forms CH3, C double bond O, OH, and one of them will become, or you can also write it CH3 COR plus, let's say this is O18. So this will become what? O18R plus the another group will become H. Acetic acid will be the another product. So this is how a chemical reaction takes place. Now what I have given you is an example of one alcoholic group. Let's say for the 5 equivalents are there, we are using it 5 equivalents of acetic anhydride. Then there will be like all 5 number of molecules of OH group will be converted into OAC. This is your ROAC. What is it? This is can also be called as ROAC. So this is ROAC. So, and one of them is acetic acid. The 5-acetic acid will be formed. So, we already knew that one of them is primary. What about the rest? Other will be secondary aldehyde groups. So, this is what it is representing you, 5-hydroxyl group. One of them was already known to us, which is primary, which was converted to COH group after being attacked by what? Concentrated HNO3 strong oxidizing agent. So, this is the difference, guys, where we attacked with mild oxidizing agent. Here we attacked with the strong oxidizing agent. Now I am understanding this chapter very clearly. Okay, see, let me give a very frank statement over here, guys. I don't care what would you think of it. It's a biological chapter, which is like a difficult for not just me, for all the person who do not have this much amount of interest in this chapter, pretty much of rotary chapter. But now once I have come up with this and explaining you everything, I am also realizing that this chapter is not that boring. It's pretty much interesting, and we are getting some of the concepts cleared even for me as well. So now we'll move forward that how we are coming to know about this straight line structure. Then another is that glucose is concluded to have. Okay, what is the glucose has been concluded with? This is the conclusion that we right now have made for the class determination conclusion. The conclusion is that aldehyde group is there. On different carbon atom we have a hydroxyl group, and the structure is stable, and 2 hydroxyl group on these are unstable on all the different carbon atoms. 2 hydroxyl groups are same on the same carbon atom, are unstable on different. Okay. That's why their structure follows this pattern. You can't make 2 hydroxyl groups on one carbon atom. That's why the only possibility we had is forming this vicinal manner. So what is a failure of straight chain? How did we not get this carbon atom? That normally the straight chain aldehydic structure following the properties or reaction shown by glucose despite of having an aldehyde group. What reaction doesn't it doesn't show? These are the number of reactions. Number 1, that normally an aldehyde group will be giving you a positive 2,4-DNP test, Schiff's base test, addition of product of the glucose, but it doesn't. Why? Because see, wherever we are over here, that this is CHO group, this is like OHH, and this is some R over here. Let's say this is one more OH over here, H over here. This goes and attack over there, and you all know about this attack. This carbon atom is now converted to OR. Another one will be OH. This kind of structure is called as hemiacidal form or cyclic form. This is a cycle now, right? And this earlier was a open chain structure, but we have seen that if it contains an openly available CHO group, which is also called as the aldehyde group, why aren't we able to make it reacted with 2,4-DNP reagent, Schiff's base reagent, NHSO3, but it doesn't give any product with that. It doesn't react very easily. That's why this linear or open chain structure is not followed very well, and this is not a stable or what should I say, it's not a stable structure. It should be existing into some different structure, which is actually the pentaacetate of glucose doesn't react with NH2OH. Pentaacetate structure doesn't react with NH2OH to form the oxime despite of having a CHO group. Okay. And the only reason what I am finding right now is this. So glucose is actually an aldehyde group or aldehyde group, or it's a hemiacetal group, right? Now this confusion might be running in our mind, like I am also facing the same. But I may come to a conclusion that if we are right now having a solution of glucose in which glucose has been dissolved in water, some amount of glucose might be in the open chain, some amount of this might be in the closed chain, some amount might be there in the closed chain classification that are also called as the anomers. Let me take you to there. So let me take you to there. So right now let's have a recap of the acetyl and ketyl, how were they formed. We know that this ROH group used to go and attack on the carbonyl carbon. This will become OH and this will be OR, and one water molecule will be eliminated out. This is called as hemiacetal. But once hemiacetal being attacked by another ROH, this give you OR group and this becomes acetal. When there is OR and OH group, it has become hemiacetal, but this is acetal group. Now we all know that the addition of alcohol aldehyde, we get acetals and hemiacetal, and generally hemiacetals are unstable, but in 5 to 6 membered ring they become most extremely stable. Generally they are unstable, but we talk about the 5 or 6 rings like we'll be facing in fructose and glucose. We'll be having a majority of the molecules existing as a hemiacetal form rather than being into some normal aldehydic or ketonic group. This is now has become very interesting, guys. Now we'll be having a proof of the cyclic structure. How does the cyclic structure exist? The very first proof that we came to know that CHO is not easily available. That's why it doesn't get easily being reacted by the 2,4-DNP of Fehling solution test. No, it does give Fehlings, but 2,4-DNP, NHSO3, these tests were not given like that. Then we have, what do we have? Cyclic structure is internal addition of alcohol and aldehyde group, and while the formation generally 5 to 6 membered rings are very much favored. So let's focus upon the first carbon which is containing the carbonyl group. The first carbon is actually belonging to the carbonyl group. Then the C5 will attack on C1. This C5 carbon, what we see, it's actually the last 2-degree alcoholic carbon as in like which is bearing the OH group, so that 6-membered ring will be formed. Anyways, I can show you how 6-membered ring is formed, but before that let us take an idea. So this is how they are formed. This structure is actually alpha D positive. Why am I calling it alpha? We'll show you that first carbon, second carbon have in same direction. This has become what? Alpha. If first carbon and second carbon have in opposite direction, it has become what? Beta. And this is the open chain structure. So open chain structure exists very small, in very lesser number of molecules will be existing over there like the open chain, and majorly it exists into beta and alpha. What I can see that beta has lesser alcoholic groups repulsion, hydroxyl group repulsion, because of being into opposite side. There is the repulsion is higher. So I think beta should exist in the more or in the highest proportion if we talk about what exists into like that, okay. Higher quantity which will exist in the equilibrium form. So at the equilibrium, 3 basically different molecules are there. One of them is alpha anomer, another one is beta anomer, another one is the open chain. Open chain exists as the least, beta because of the lesser repulsion will exist in the most, and alpha will be the in between of these two. But yes, alpha and beta are the dominant one, okay. So like 62%, 32% like that, but we'll come to know about it. Let's take an idea of Haworth projection. How is it made? So Haworth projection, usually it is difficult to show, but I have a very smart move from here that you can understand, and then you can form whatever it is, okay. I'll explain you. So first, what did we have? We had CHO group, we had OH group over here, we had one more OH group over here, we had OH group over here. In the one step, you can understand all the Haworth projection and whatever the projection is there. Just allow me a sec, right? I'll explain it. What is this looking like to you guys? What is this? What molecule is called? It is called as D positive glucose molecule, which is an open structure. Now, from this open structure, we see that in equilibrium, this group will go and attack over there, as I told you, fifth one and 2 degree. So, what kind of structure does it form? See, so there, this is like this is the carbon atom, which will be becoming OH. This is H. This is just first carbon atom. This first carbon atom we are just showing into this way, will be connected with over here. So this is the first carbon atom, second carbon atom now. Anyways, I can give you an idea. This is the first, second, third, fourth, fifth, and sixth. But over here we have this much as first, second. Let me first draw the whole structure and then we'll show you. Third one will be having in opposite. Fourth one and fifth one. Fifth is already connected with this. Then the last will be how many? 1, 2, 3, 4, fifth. Like that. This is how this whole structure looks like. So this is actually 1, 2, 3, 4 and 5 and 6. This is one of the structure where we can see that this is called as anomeric carbon. This first carbon. So this first carbon is carbonyl carbon and having this thing into right hand side. This is called as alpha. This has become alpha D glucose. Now what we are calling it alpha D plus glucose. Why am I calling it alpha? Because the first carbon atom is having, the acetal form is having this OH group in the right hand side. And now if I talk about the same group and I form the same compound like this, there we have the first OH group in the left hand side. This one the hemiacetal form, and this is like the same only OHH, then in left hand side, then in right hand side, and this is the fifth carbon atom which is having the hemiacetal form with one H over there, and this is your CH2OH. Now what is the most important part that we have to observe from here? What do you think is the most important part that we have to observe is, sir, okay, what has it become? This has become beta D plus glucose. Okay, the nature is still plus. So now if I look at them, let us look at that. What these two are, they are different, they have different composition only at first carbon. So 1, 2, 3, 4 and 5, this is 6. Only one carbon atom they are differentiated at. These two are called as these two are called as anomers to each other. Now I will be drawing their cyclic or cyclic projection, Haworth projection. So cyclic projection is not possible for this. This is only possible for this. So this is, now I'll draw Haworth projection of these alpha and beta form. I will try to draw the Haworth projection of these two form of alpha and beta. For this, take this kind of hemiacetal form, we have to write it like this. This is actually your, this is the hemiacetal form, the same form. This is your first carbon atom, second carbon atom, third carbon atom, fourth carbon atom, fifth carbon atom, and this has been attached to CH2OH. This is the sixth carbon atom. This will be H. Now whatever it is in right hand side, just make it downwards. Right hand side will go downwards. So first atom will be having downward. This is OH, this is H. Second one also is in right hand side. This will come up as OH, this will come up as H. This third one is having left hand side, so this will go as OH, this will come up as H. This will be going as fourth one. Right hand side will come at down, up. So basically what we have to follow is this, that whenever we are right hand side the OH group is there, in Haworth projection that will go where? Down. If there is anything in left hand side in open chain structure or like hemiacetal form, then left thing will go and up in the Haworth projection. Just follow this part and then try to draw the another structure possibly from here. See, this is oxygen, first carbon, second carbon, third carbon, fourth carbon, fifth carbon. 1, 2, 3. So this is actually OH is coming in left hand side. Left hand side will go in up. This is down. This is down. This is up. This is. Can you see this up down is making actually it is more stable than the another one because it is having least repulsion between two OH hydroxyl group. As you can see, this will be your OH over here, H over here, and this will be CH2 OH and H over here. So this is the most stable structure that we have seen, beta. These two are called as anomers of each other. Now, please, if you can write. Actually, I didn't want to disturb the already made structure. That's why I took another example and explained you all the part related to it. Okay, and that's how I explained all the parts related to it. Fine, till here we are all at the same page now. Now I'll be taking you to the next portion of this chapter. This is what the Haworth projection we made, and very easily we all have more or less completed this part. Very easily we have covered this part. Now we have another thing that is called as how did we come to this structure? This is a pyran looking like structure called as pyranose, came from pyran. This is pyran, how it is, it's look like. So from pyran we got this structure called as pyranose structure. Glucopyranose we can call it. Now let's see some of the questions along with the structures we just have made. D-galactose, D-glucose, D-mannose. What is the difference that you find? Let's say if I'm talking about glucose, out of this glucose, heavy glucose, we see that the fourth carbon atom, 1, 2, 3, 4, this is having a different orientation, right? Isn't it? And if we see the same thing in the mannose in there, it's a C2 epimer. See, this is in this. Rest everything is the same. So what do we conclude out of it? That all three are aldohexose first of all, which is true. D-mannose is C2 epimer of D-glucose, true. Galactose is C4, true, and all are correct. D is the correct answer. Try another question. Which of the following reaction proves that glucose contains an aldehyde group? See, if we have an aldehyde group where it must get oxidized to COH group. So reaction with concentrated HNO3 does two things. Oxidizes to 2 degree OH group also. Not 2 degree, it's a 1 degree, the primary group over there, and it also does CHO group to be oxidized to COH. So this is not a correct thing. The only correct thing is bromine water, because what does it do? If this is the carbon atom with OH group and this is 1 degree, this Br2H2O has no reaction on that, but only CHO group under the influence of bromine water gets converted into COH. So I think B should be the correct answer other than A. So not A, C. B is correct. Next, anomer, as we already have explained it, beta and alpha are there. What is the difference of that? See, we already have made that part of this structure which is called as hemiacetal form. Now when this hemiacetal form, the first carbon atom, which is the carbonyl carbon, is having an OH group. Now whether the OH group is in right hand side or downwards. See, as I told you, this must be taken very carefully, that right will go in down. This is what? This is in Fisher projection. This is what we are in Haworth projection. And the left thing will be going to up. See, this is in upside and left hand side. This is beta. And beta is more stable, okay? So epimer and anomer, they both are actually diastereomer of each other. Glucose has two crystalline forms. One of them is called as alpha glucose, another is called as beta glucose. The melting point is 382 to 345, which is lesser, and it has a higher boiling point. Higher melting point, because you know sugar-like structure is there. They all like crystals. So usually I told you alpha is less stable than beta because alpha had two OH groups, like on first carbon and second carbon at the same side, and that is what the repulsion makes it less stable than beta one. It is thermodynamically more stable form. And 5 and 6 member hemiacetal are stable, okay, that we know. Alpha and beta are actually C1 epimer of each other and formed in the sugar tree, and the one formed in sugar tree were in C2 epimer. So C2 epimer are actually two different kind of compounds, but C1 epimer is the same compound with different hemiacetal forms. So that's how they are different actually. Look at this, alpha glucose and first and second carbon are like in similar directions. Repulsion might be higher. This will be causing it lesser repulsion. And there we are having a higher repulsion. Now, talking about the equilibrium that exists between the alpha and beta form, let's talk about that. So, the open chain is very less in the quantity if let's suppose 100 number of molecules have been picked in a solution. So, out of these 100% or 100 molecules, 0.02 will be there, which might exist in the linear or the chain form. Around 64 of them will be existing in the beta form, as I told you, and alpha will be 36%. So, learn it's an important data. 36 and 64, and this is like negligible existing over there. The reason is very much known to us. Next is called as mutarotation. Next topic is called as what? Mutarotation. So let's have a look on what mutarotation is and then we'll understand it. So the specific rotation of pure alpha D glucose or beta D glucose changes over time to time to reach an equilibrium value. So this phenomenon is called as mutarotation. The meaning of mutarotation is that initially, let us suppose we only had the alpha form. Some of the alpha form will be automatically be converted into beta form, and finally will reach to an equilibrium where 64% of the beta form and 32% of the alpha form will be existing in stability. So under that, when initially we saw that alpha form had 112 of this specific rotation, positive direction, which later on changed to 52.7, and specific rotation of 92 degree was there, 19 degree was there. So ultimately the solution containing, let's say, 52.7% of the 52.7 degree clockwise rotation, but that of individual forms were 112 and 100 only 19, but equilibrium maintains at the 52.7. That is what it is called as the mutarotation, that individual form of the this hemiacetal forms or Haworth projection. Right now we are taking alpha and beta form, or they are also called as anomer. These anomeric forms gets converted to each other and have different specific rotation, but once they reach to the overall equilibrium, their overall this what should I call it here, this is a specific rotation changes, and this change in the specific rotation is called as the mutarotation. Correct? That's why it has been said that the open chain has an intermediate of that equilibrium. How many compounds will undergo mutarotation? What do you see out of these? How do we decide that which one of them will go mutarotation? So guys, as you all can see, in this structure, this is the first carbon atom. In this structure is another carbon atom. But I see that let us suppose if you are picking their pure forms, they will be automatically be equilibrated, undergoing into another form also. So the correct answer is all. Those who can show anomeric structures, anomers, they all will be undergoing this part of this. So let us look at this. This is the first carbon atom. This is the first carbon atom. This can exist into OH down and H up. This can also exist into, these two are showing the mutarotation. Let me take you to the another example. So this also is the first, second, third, fourth and fifth. So I think this is the first carbon atom. Over here, this is the first carbon atom, and they also show anomeric forms. Okay, up OH can go to down OH can go to up OH, and ultimately they will be equilibrated and finally forming this structure. Actually, there is nothing complicated over here. These two actually you see are actually the Haworth projection of hemicyclic structure, or these two are the Haworth projection of glucose, and the rest of the two that you are watching right now over here, these two structures are actually the Haworth projection of fructose. So glucose and fructose, right? Let's see a question. So which of the following represents the anomer of the compound shown? Which of the followings represent an anomer of the compound shown? So anomer will be basically decided using the first carbon atom, that we see that this is the first carbon atom or the carbonyl carbon atom. So anywhere you find a difference over there of the groups, they will be what do I call them? Anomer. So see, this is OHH. I think B is the correct answer. This is the same. This is actually different, but I see there's some changes in other as well. So thus have been made changes. Yeah, these two have been changes. This is exactly, the rest should be same, right? And only this should be changed. All must have same configuration. B is the correct answer. Next question, which of the following pair represents anomer? So again anomer, we are talking about anomer. So anomer cannot be identified under open structure. Only in cyclic structure we can find out using this carbon atom 1. This is 1 and having this in opposite direction. This is the correct answer. But this is a 1. This is 1. Okay. Wait. Do we have anything which has been changed apart from this? Yes. This has been changed. So these are not anomers, they are epimers. So this is the incorrect answer. This is absolutely correct. The rest should be same. Always apply the rule. The rest should be same. Only anomeric carbon must have different orientations. Rest should be the same. So that is how we studied the structure of glucose very well till here. Hopefully all of you are getting me and enjoying the lecture as well. Now let me take you to the preparation. How is glucose prepared? There is one very simple way to prepare glucose is from sucrose. Just simply sucrose undergoes dissociation reaction. So commercial method is to prepare it from starch or cellulose, which are actually made up of, these are polysaccharides made up of only glucose, which is also alpha D glucose they are made up of. So this alpha D glucose gives you so N-1 water molecules are there under acidic conditions. This gives you glucose. And if you talk about the hydrolysis of cane sugar, this is another first order reaction. You all know pseudo first order reaction. Sorry, producing glucose and fructose. Simple, that's it. It's completed. Now we'll see some of the chemical reactions of glucose. So you all know glucose under reduction with HI and red phosphorus, which is the strongest reducing agent, completes a reaction and gives you a carbon chain of 6 member, which is called as N-hexane. N-hexane with over there, strong reducing agent, right? And similarly, catalytic reduction, if we do it using Ni or CN, so this is something that is used to convert the aldehydic or ketonic or any oxidized group into its reducing version. So this will be converting into CH2OH. So we will be getting all OH groups. So this is what it is happening with the mild reducing agent. This is happening with the strong reducing agent. Strong reducing agent is actually converting all the alcoholic groups into alkane, and H2NiPTPD or NaHgC2OH or NaBH4, LiLH4, this will be converting the CHO group into CH2OH. Third reaction is HCN, cyanohydrin. We know that one carbon atom, that is your carbonyl carbon atom, will be converted into one containing OH group, another containing CN group. This is what we call as cyanohydrin. This is how cyanohydrin is formed. Now this cyanohydrin can be further reacted with SnCl2 and 2HCl. Reaction is called as Stefan's reduction. Under the C triple bond N group gets converted into CH2OH. So you can see your final answer will be all of them are CH2OH, and one extra carbon atom has been introduced because of this CN group. So that's how we will be getting one extra carbon atom. Cyanohydrin can further be, cyanohydrins can also be, you know what's going on here, HCN, why we are having two different things here. Okay, why are we having different forms? This is C1, C2, amoeba. Over there you can find it. This is C2 epimer actually. No. Are you sure this? Anyways, we got the reaction, that's it. Another reaction with hydroxylamine, another similar reaction that is actually happening with the presence of this group, and you will be getting a glucose oxime. Glucoxime. Oxidation of glucose is bromine water, mild oxidizing agent. It gives you gluconic acid. But if the same reaction happens with concentrated, this is a mild oxidizing agent, and this is a strong oxidizing agent. A concentrated HNO3 strong oxidizing agent converts it into saccharic acid, or also called as glucaric acid. Next is the reaction with HiO4. This basically oxidative cleavage reaction I have already shown you. So whenever you find this kind of structure somewhere, this reaction with HiO4 gets an oxidative cleavage, forming a compound like this. Let's suppose this is a hydrogen atom attached over here. The same reagent, this has been converted into OH, C double bond OH, C double bond OH, like this. And this reaction also works if there is already existing COO group is there, and this carbon containing the OH group over here, like this, and one of them is, let's say, hydrogen. This will be converted into C double bond OH plus will be converted into CO2. Further oxidation will be taking place. This is some key points actually I am reminding, that what happens when we react it with HiO4, okay, OSO4, osmium octaoxide also gives you the similar reaction. That's it. So these are the number of reactions we study for glucose. Now there is one more thing that is called as a test of glucose, and glucose gives you a positive tolerance test, but it does not give you 2,4-DNP test. It also gives you Fehling solution test. Silver is actually reduced tolerance reagent, can be also be written as silver complex, like this, AgNH2 whole NH3 whole twice with a positive charge, and then OH negative. So this basic ammonium, basic silver ammonium complex reacts over there, and Ag is basically what? Reduced, and this has been oxidized. So this portion is called as an oxidation. This is a redox reaction, you can see, and this silver from its positive 1 state to Ag is actually reduction. Similar thing you will be observing over there with the Cu 2 positive. Cu2 positive is converted to Cu1 positive over here. So this reaction is actually happening with CuO. Next is OSA zone formation, one of the very important reaction, and let me mark a star over here. Why? Because questions have been asked previously. See, this OSA zone formation takes place with the help of phenylhydrazine. You all know about phenylhydrazine. Hydrazine is NH2 group. One of the hydrogen is replaced by phenyl group. It becomes NH2 NHPH. This is called as phenylhydrazine. Now, this NH2 group of phenylhydrazine attacks on the carbonyl carbon, forming a compound called as 2,4-DNP, which is again phenylhydrazone. This hydrazone can also be attacked, or this reaction can also be taking place by two of the important terms. One of them is this becomes this secondary, which is right now in the contact with CHO, also becomes a carbonyl group with one of the phenylhydrazine. That's why we take generally 3 equivalents over here, and no need to go for the very much research into this segment, only just keep learning. One of the phenylhydrazine is required to convert COH group, second carbon, into CO group, which also has been attacked by 3 equivalents and forming this compound. One of them is this, another one is this, and where is the third one? Third one is used in 3 moles of phenylhydrazine is actually first mole of this converts this C2 carbon into ketonic group and then reacts with this forming PHNH2, this is aniline, ammonia and water. Next comes monoalkylation. Monoalkylation, you all are aware about the alkylation reaction. In alkylation reaction, we take ROH group and react it on the first OH group where this reaction takes place. This converts into OCH3. Under acidic condition, this water will be eliminated out and then attacks the Me like this. The OMe is the product over here. This is called as monoalkylation. If you perform the same reaction, multiple alkylation may occur because there are plenty of OH groups over there. Then polyalkylation, all of them will be converted into OCH3. All OH are converting into OCH3. But this reaction takes place, then this has been taken into access and Ag2O as a catalyst. Now look at this reaction, guys. Take an idea. The same thing now over here is in AC2O pyridine, that everything is converted into OAC, OAC, OAC. Wherever OH was there, it has been converted now OAC. Reaction with enzyme. If we introduce glucose to zymase, it converts into ethanol. This is how the ethanol is prepared using glucose. So first of all, what we do, we take a bigger carbohydrate such as sugar or sucrose, which is right now, which we can be easily obtained from the sugar-rich fruits such as plum, grapes, in fact mango, or so many fruits like that, and then they are undergoing fermentation under yeast, giving first of all converting this whole molecule of sucrose into glucose and fructose, and this glucose gets converted, even fructose under the influence of zymase as enzyme gets converted into alcohol, ethanol, which is an important ingredient of all the alcoholic beverages. And then reaction with NaOH and CaOH whole twice, reaction with soda lime. Actually the soda lime reaction will do what? No idea. What does it do? Okay, it's simply a basic medium. It's simply causing a basic medium which asks glucose structure to be tautomerized. So tautomerization occur, due to which aldehyde and ketonic both form exist. See, mannose, it converted back into mannose. Even meanwhile, it can also go to aldehydic and ketonic forms. So now we have give the compound is enol form of the given compound. What we see is in enolic form of what? So you know about enol. I think all of them are correct answers. I'll explain this question. Just allow me a second. I'll be coming back and joining you after getting some water. So you try this question until then. So we have a question in front of us and we'll try to solve this enol form. Okay, let me take you to this question. Actually, I was explaining that this enol form can take you to the formation of either one of them. How? Because this is alpha hydrogen. So let's say this hydrogen participates like this. So anyways, we'll explain this part when we'll be coming in fructose. Okay, let me remind you that by that time only, because now let's not waste the time. It will be repeatedly coming. It will keep on coming with the multiple basically concepts. Okay, a similar question. D negative erythros and D negative 3Os are separated and they are now reduced with the NaBH4 to give a products A and B. So which of the following correct statement about A and B? So what A and B will be there? So A and B will be diastereomers of each other. They will be no doubt erythros 2 1 up. So D negative erythros, how does it look like? This is D erythro, OH, OH, CHO, this is CH2OH, this is H, this is H. This is basically D negative erythros. If I react this thing with NaBH4, it will be giving you CH2OH, CH2OH, OH, OH, HH. Oh, that was unnecessarily. Now, if I take this another example with OH and 3Os we are talking about, this will be definitely in OH direction. This is H, this is OH, this is CHO, CH2OH. This with similar compound will give you CH2OH, HOH, OHH, CH2OH. Look at these two. One of them is optically active, another one is not. This has a, as you can see, this has a plane of symmetry. So this is optically inactive. This is optically active. It will be having RR and SS in enantiomeric forms. No element of symmetry over there, no plane of symmetry over there. So what I can see, this is A actually, this is B. So A is optically inactive, B will be active. I think C is the correct answer. The reagent which forms crystalline osazone, which forms osazone? I think phenylhydrazine. 3 equivalents were used. Osazone can be obtained by, this osazone can be obtained by, so we are having allose, glucose, mannose. So mannose and glucose will be the similar one because C1, C2 monomers. Rest of them may have different number of carbon atoms. Even I remember allose has different one. D is correct. Yeah. Let's have another important compound called as fructose. Hmm. So guys, let's not waste the time. We'll simply reach to the ketohexose form, which is the linear form. Linear form is looking like bit of this. Glucose and fructose, both of them look like very similar to each other. So like if I want to give you an example, so this is how we used to draw the structure of glucose CHO. The formula was still the same, C6H12O6, exactly the same. This is actually alpha, this is not alpha beta, we are not supposed to write it because that is actually comes in hemiacetal form. It's simply D-glucose. And now I'll draw fructose, so CH2OH is already there. One carbon atom is there. Then this is how, same structure, rest is the same structure. This is called as D negative fructose. This positive and negative nature is actually representing its optical nature, okay, whether it is dextro-rotating or levo-rotating. On that basis it is explaining. What other we are finding in glucose? So there could be alpha and beta. So there is like a five-membered ring will be formed here. Five-membered ring will look like over here like this. So there we have this OH group in right hand side will become alpha, and this OH group in right hand side will become beta. So how we know that it exists as a five-membered ring and as a pentagon? So keep the oxygen on top of the corner of pentagon bonds in the vertical line, blah blah blah. Anyways, this is what we have already done. So even if you need it, I can explain you. This is the first carbon atom. Second, which is the carbonyl carbon. This one is the carbonyl carbon. And we are right now seeing its hemiacetal form. Hemiacetal, or you call it hemiketal form. This hemiketal form actually looks like this. Next, Haworth structure of fructose. Haworth projection, we also know that one of them is alpha, another one is beta. These two are called as anomer to each other. Both of them are levo-rotating with a negative sign, and then alpha D group. Alpha D will be having OH groups under. This is second actually carbon atom with OH, and this is actually their two are opposite to each other. And there we have OH over here, OH over here in similar direction. Similar becomes beta here. Okay, got it. Actually, we have to see at the bulkier group. So this is how we have to check it. Bulkier group we have to check. This is the OH group and this is the CH3OH. This is actually more repulsion. This is actually in more repulsion. There the bulky group is here. Here the bulky group is here. Here we are having lesser repulsion. Relatively lesser. So beta is again more stable than alpha. This structure is derived from the furanose structure. This is called as furanose structure. Haworth structure of fructose. How does the Haworth projection of fructose come? You all know. So alpha and beta forms are there. Fructose with its beta structure has two OH group in the same side. These structure are called as furanose, and they are fructose derivative. So fructofuranose. Alpha and beta form, you can see alpha and beta forms. Okay, that's how they decided alpha and beta. Now we have some chemical reactions of fructose. Number one, in basic condition. Number one, try to understand, in basic condition, it can be converted into either of the forms as in, please check out, it can be converted into, this is what its enol form is. This is the enol form of fructose. This enol form can go to glucose, mannose. So that is why we say that the aqueous solution of fructose can also give you the Felling's test, Tollens test. Why? Because it also have some conversion into glucose, and some of this glucose form react over there and reduces the Tollens reagent. Let's move forward. These are some very easy things right now. Once you have covered the portion I taught you in case of glucose, then fructose is quite easier to us. Then we have glucose and fructose generally show similar kind of reaction. Alpha hydroxy carbonyl are known to show the positive result on Tollens test also, and that is why I told you that this carbonyl, this although fructose contains the ketonic group, but still gives you Benedict and Tollens test positively because of the conversion into aldehyde group, just like from here. Glucose and fructose show positive test of, okay, fine. The open chain fructose is possible number of optical isomers are how many? So how many number of atoms can you see? This is CH2OH, this is C double bond O, this is CHOH, this is CHOH, OHH, 1, 2, 3, 4, 5 and 6. How many of chiral carbon can you see? 3. So 3 to the power 2 will be 9 is the correct answer. Number of optical isomers. I think 9 should be the. In open chain structure, the number of possible optical isomers. So how many chiral carbon can you see? I only see 3. So 3 raised to the, okay, wait. It's 2 to the power n. So 2 to the power 3 will be the 8. 8 is your correct answer. B. Like that we have to do. Which of the following functional group is not present in cyclic structure of fructose? Does it have any keto group? No, keto group is not there. Keto group is now converted into hemiacetal form, OH and OR group. Ether group, does it contain ether group? Yes, it is there. Secondary alcohol is there, primary alcohol is there. Keto group is not there. A question that came in JEE Main 2025, but this year only this question came. So we'll try to see, we'll try to look out of this question, which looks a good question, by the way. Question looks quite good. The carbohydrate ribose present in DNA. Okay, this is about actually ribose. So we'll cover this question later on, guys. What do you think? Or let's see if any one of them is known to us. So carbohydrate of ribose, pentose sugar, true. Present in pyranose form, pyranose, glucopyranose. Actually, it's a pentose sugar is there. I don't know it present in pyranose form, but I think it is present in furanose form, not in pyranose form. So let me call it a false as of now, and it's D configuration. So yes, This is true. Capital D, OH group is in the right hand side at the last chiral carbon. It's a reducing sugar because all the monosaccharides are reducing. So this is the true statement. So we can see, and E in alpha anomeric form. Carbohydrate ribose in DNA is present in alpha anomeric form. Let me check the correct answer. So A, C, D are correct. So definitely it's a false statement. And we'll check out this part whether it is alpha anomeric. Actually, beta anomeric form is always more stable than alpha because of the lesser repulsion, and that's why this might also be existing into beta form, not in alpha anomeric form. So correct answer is C actually over here. Considering these statements, C should be the correct answer. It was a question from 2025 in JEE Main. Okay, let's see another such question. Exactly the same question came in 2025. Question came in 2025. Fructose does not contain any LD group. It still reduces this, which is a true statement. And the presence of base, in presence of base, the fructose undergo rearrangement to give glucose, which is also true, and a correct explanation also. Both statements are true. Both statements are true. C is the correct option. Then we have another question that this given number of molecule, the incorrect statement regarding to this molecule is what? So we have to identify the incorrect statement. This is the molecule. Actually, this is glucose only. This is a D glucose, I can see. D plus glucose. It can be oxidized to dicarboxylic acid, which is false statement. Actually, this is the only incorrect statement, right? False statement. Despite the presence of CHO, it does not react with Schiff base, which is true because it actually majority of this exists into beta and alpha form, which is hemiacetal form, which does not react with the heavy Schiff base, which does not react with the secondary amine to form the imine. Primary amine actually react there to form the secondary imine, which is called as Schiff's base. Will coexist in equilibrium with two other cyclic structure. Does it coexist in equilibrium with two other cyclic structure, which is also true. Alpha and beta, which are called as the anomeric forms, alpha and beta, where happens the mutual rotation. There happens the mutual rotation. So it has a 4 asymmetric carbon, as you can see, chiral carbon. You have a count of 4 chiral carbon, 2 to the power 4, 16 number of these isomer exist over there. So this is also true. The only correct answer is A, because it has been asked the false statement. Concentrated HNO3 could have reached to 2 carboxylic acid group over there. One cannot lead you to over there. Another question. The following are the correct structure of L-glucose. So I told you once that L-glucose is actually the mirror image of D-glucose. So first you should know how to form the D-glucose, then you have to convert it to L-glucose. So first I'll make D-glucose. How does D-glucose look like? This is CHO. This is right hand side OHH. This is left hand side OHH. Again right hand side OH. Right hand side OH and H, and this is CH2OH. Now take a mirror image. This is actually your D-glucose. Take a mirror image of this compound. This will be CHO, OHH, HOH, OHH, OHH, and then CH2OH. This has become what? Capital L glucose. Now, can we identify the correct structure of this compound? Can we? Yes, we absolutely can. So, this is how it looks like in CH2OH. Then OH right and left. I think B is correct. See, I tried to match it with the L-glucose. I made it over there. And I found the correct option is actually D. Can I get the correct answer D? Yes, D is the perfect answer. Guys, till here, as I told you that saccharide or the carbohydrate part is even a bigger part in whole this chapter. So till now we have finished for monosaccharide. Now I'll take you to the disaccharide, and then after that we'll be coming to polysaccharide. Let me take you to disaccharide. The name itself suggests that if you add water in them, So it will give you two monomers, monosaccharides. 2 units it will be giving you as a monosaccharide unit. So one of them, these are some important examples by the way. Sucrose, lactose, maltose. These three we have to know very carefully, and we also have to know which anomeric form do we use over there. So this is alpha D glucose plus beta D fructose, sucrose, beta D galactose plus beta D glucose. This is your lactose, and maltose is alpha D glucose and alpha D galactose. Glucose and glucose only is your maltose. Lactose is beta D glucose and beta D galactose. Alpha D glucose, alpha D glucose, alpha D glucose, beta D glucose. Now learn it ASAP. Learn it right now. Do it ASAP, guys. Right now only. So now I'll show you the glycosidic linkage. How are they formed? So how are they formed, by the way? This glycosidic linkage is actually also called as the ether linkage. And I'll also show you how this linkage is formed. How is this ether linkage formed? Okay, there is a proper way of forming this ether linkage. So there is one, let's say OH group is over there, and there is one OH group is over there to another carbon atom. They remove water out of it. They get connected with this O group. This oxygen as an ether you find is called as a glycosidic linkage, or called as ether linkage. This is the glycosidic or ether linkage. So this could be beta beta also, alpha beta also. Now I will directly take you to glycosidic linkages between the individual maltose, sucrose and lactose. So I'll first explain you about the sucrose. Okay, let me draw it about how sucrose can be shown with its glycosidic linkage. We know this has been formed by alpha. So I'll write it over there. Alpha D glucose. First of all, I'll make alpha D glucose. This is your alpha D glucose, OH, and OH on the downside, it was there, downside. So this is basically your alpha D glucose. This is alpha D glucose, and now we will revert that group and we'll try to make an opposite of the way, and it will be exactly the same molecule. We are not taking its enantiomer, but we have to draw it such a way that we can show it C1C4 bonding. So C1C2 bonding takes place over there. So this is how the structure of pyran looks like. Furan structure, furanose. So let us say this is the first carbon atom. On alpha, this is beta D galactose, fructose, beta D fructose. Let me also check once again. OH is there downwards. So there we have its OH group. CH2OH is out. Next we have this OH over here, H over here, OH, H, above, down, down. And this might be CH2OH, right? No, H. The first, actually, this is how it look like. So, yeah, how can we see this is down, above, and then okay, mistakenly I took the wrong. 2 carbon has it down, then 3 comes at down. And then at last carbon atom we have CH2OH rather than having the OH group, right? CH2OH and then H. This is your CH2OH. So this is actually the structure of beta D fructose. So from alpha D glucose, beta D fructose. Now you can see these two OH group, one of the molecule of H2O will be eliminated out and forming a final structure. So how does the final structure look like? Let's see. The final structure looks like into this way. अरे यार हट. Okay, now I'll try to make this structure. Please check it out, guys. Rest of the group we have to keep it exactly the same. So this one was hydrogen. There we have the OH and H group, OH and H group, OH and H group, and there we have the CH2OH with one hydrogen. And now look at the remaining amount with the fructose group. C1 we have beta D fructose, so we'll keep it above CH2OH group. We'll be having this at downwards, we'll be having it at the upwards, and finally CH2OH and one hydrogen over here. Like that. Please have a look. Please look at the structure. So this is called as the C1C2 glycosidic linkage. C1 or C4, 1, 2 I guess. That's why this carbonyl carbon, you can see both carbonyl carbons are engaged, okay? You can check it like both carbonyl carbon are engaged into glycosidic linkage, and that's why it is a non-reducing sugar. That is the beauty actually of this structure. Okay, fine, then that is how the structure looks like. Similarly, guys, please learn it. This is the C1 C2 glycosidic linkage of alpha D glucose and beta D fructose. This is a in maltose we have C1 C4 glycosidic linkage between alpha D glucose and alpha D glucose only. This is alpha D glucose plus alpha D glucose. Check it out, this is alpha. So on second we have this on two atoms. First is on right hand side. This is actually like that. You see, this is first carbon, this is the fourth carbon, this is C1, this is C4. Now talking about the sucrose, we also have known that this is a C1 C2 linkage, but between alpha D glucose to beta D fructose. That is what we have to learn. And in lactose, we can see, look at this structure. We have beta D glucose plus beta D galactose, and that structure is also having C1 C4 linkage. So C1 of the glucose, C4 of the galactose. That's how they participate. This is your beta D glucose, this is your beta D galactose. Complete. These three structures are the one that we have to know. Now I'll take you to the next examples and some questions on these structure. Then we have the reducing nature of disaccharides. So reducing nature is all because of the free availability of the group, that the free availability of the carbonyl group, whether it is in the form of hemiacetyl form. The OH group which is attached to this carbon atom easily is accessible, and that is what it is engaged into. Sometimes it participates into the glycosidic linkage as well. So if it is participating in glycosidic linkage, if let us say the carbon atom of carbonyl group itself is engaged in glycosidic linkage, then it cannot reduce down to the tolerance region. It will become a non-reducing sugar. And very one example of that is our sucrose. Because of alpha D glucose and beta D fructose, the carbonyl carbon is engaged in the glycosidic linkage, and rest other disaccharides are reducing in nature. Clear, guys? Moving forward, so all the reducing sugar is the one that can reduce tolerance reagent and itself can be oxidized to the carbonyl to the carboxylic acid group. Then a sugar is classified as reducing sugar if it has an open chain with forming an aldehyde or hemiacetal free group over there, and all the monosaccharides are reducing in nature. A non-reducing disaccharide, which is like both anomeric carbonate are tied up, and the very one good example of them is sucrose, non-reducing sugar. In maltose and lactose hemiacetal form, they have one free atoms in this second saccharide unit, second monosaccharide unit of disaccharide, and the structure of both anomeric carbons are tied up in glycosidic linkage. In the sucrose, so this is called as this has become now non-reducing sugar. Now let's try some questions on this topic. Sucrose, we have to study it in a bit detail. We already have done it, but let's take another example how we are basically doing it. So you see, first of all, they are having alpha D glucose. Okay, this is how the alpha D glucose look like. So alpha D glucose basically came from this structure this is how the oxygen bond is there of hemiacetal form. This is the carbon which is having a right hand side alpha D glucose, right hand side. Second carbon also has in right hand side, then third in left hand side, fourth and fifth into the right hand side, but fifth one is already connected over here. So the last one will be having simply CH2OH. There we have the hydrogen. This is actually alpha D glucose. This is alpha D glucose. I'm trying to make beta D fructose so that we can compare where are they connecting exactly. So now I'll draw beta D fructose. So beta D fructose. So I have to show it in this way. So let's say in this way only I'm drawing it. This is how CH2OH is attached there. We have to take beta form. So this is how the beta form looks like. This is first carbon, this is second carbon. This is the third carbon always headed at the left. Fourth and fifth is actually attached over here. And this is how the sixth look like. This is the structure of beta D fructose. Let me number them also in order to remove the confusion. Six. That's how it is represented. Okay. Now, out of this representation, we got to check it. See, we have to check it where we are attaching these two structures with. Okay. So this is, when I mentioned it, it's the number 1 carbon atom. And this is the second carbon atom where we have this 1 carbon. So this is how that is having a C1C2 glycosidic linkage. 2 structure is here. 3 we have. So we have just rotated the structure. Seems like we have just rotated the structure. Actually, it used to look like this. Okay. Let me try this structure if I can make it. This initially structure used to look like this. So there we used to have CH2OH. Here we used to have H. See, we had OH in the downside. Then on second carbon atom, this is the second carbon atom, this is the first carbon atom. Third, we simply have this OH above, H down. Then we have OH, H, and finally it is having CH2OH, and this is H. Like that, the structure was made. Now we have just did what? We just have rotated it. We just have rotated it like this. Rotated by 180 degree. So now, because earlier, see, you can check out, you can see this. This is C1, this is C2, this is C3, 4, 5 and 6, but now it has become, see, 1 has come here after rotating and 2. So now everything is changed. Whatever the after rotating it 180 degree, if down has become up, up has become down. This is how it is happening now. Up has become down, down has become up. So that is it. So you can see that none of the hemiacetylic carbon, or we can also call it carbonyl carbon, is free here, that can be oxidized to carboxylic acid group by Tollens or Fehling solution. That's why we say that sucrose is not reducing in nature. Sucrose on hydrolysis gives you 2 products, that is alpha D glucose, beta D fructose, Alpha D glucose is actually dextrorotatory in nature, which has a glucose has a 52.5 degree in positive direction, and fructose has a negative of 92.4 in negative direction. And overall, when they are mixed, they give you a very different type of rotation. So hydrolysis of sugar gives you basically formation of inverted sugar. We call it what? Inverted sugar, because see, cane sugar is there. Cane sugar is dextrorotatory. Let's say this is a dextrorotatory, this is a dextrorotatory, this is a levorotatory, but their mixture overall becomes levorotatory. This is called as inverted sugar. That's why we call it inverted sugar, because initially the sugar had a dextrorotatory in nature, and it has later on become levorotatory in nature right after mixing it into water or upon hydrolysis. So that's a reason we give it. Then maltose, we talk about maltose. We have simple C1C4 linkage there. This is how it is mentioned: 1 2 3 4, 1 2 3 4, and this is even C4 linkage, which is between alpha D glucose, maltose, and maltose has alpha D glucose and alpha D glucose only. Lactose has beta D galactose and beta D glucose. So beta D galactose is written at first, then beta D. So C1 of beta D galactose we have to use. No, C1 of glucose unit. Wait. The free carbonyl. Okay. This is the free, basically carbonyl carbon in the glucose structure. Now let's try some question, and then we'll wind up this complete session of carbohydrate. We'll take a break, and then we'll start it from the remaining part of this chapter, that is your alpha amino acids, proteins, vitamins, and nucleic acids also. The correct statement about the following sugar X and Y is. So what we see basically, we have to check it. These two are the glucose units only, glucose or probably galactose also, but we have to check it. But I can see one more part over here, that this is a C1 carbon atom, this is also a C1 carbon atom, and remember that this C1 C2, this is C1 C2, and these two are carbonyl carbons, due to which no carbonyl carbon is available. They both are now part of the glycosidic linkage, and that's why this is non-reducing. This is now non-reducing. Probably the structure of sucrose we are right now dealing with non-reducing. Check out this part. This is actually C1 carbon atom, but this is actually C4 carbon atom. This is the available carbon atom. That's why this is reducing in nature. This is reducing in nature. This is the reducing sugar. Now check out the correct answer, guys. One of them is non-reducing, another is reducing. So X is actually non-reducing, Y is reducing, B is correct option. The correct statement about the lactose, you remember lactose? Alpha D galactose and beta D galactose and beta D glucose. So it consists of one galactose, one glucose, true. Mutarotation is not possible. See, it is false, because anomeric carbon is available over there, which can be equilibrated back to the required basically structure. Then anomeric carbon is attached to fourth carbon of beta 1 and beta 4 cycloglycosidic linkage. This has been written down as fructose, which is a false statement. So is correct, we have to give a, I think A is correct, no? Is a non-reducing, it is also false. Only A is correct here. Let's see the another question. Which of the following disaccharide will show you mutarotation? all of them show you the mutal rotation. Wherever you see the availability of the anomeric carbon, that will give you a mutal rotation, because mutal rotation is nothing but the conversion of its optical activity from one to another just in the equilibrium solution. So initially, let us suppose you are having alpha D glucose and it has a 53 point something, let's say in positive way, and beta has its all basically optical rotation. So once they will be capped at some place, it will be automatically converted into its exact equilibrium state where alpha, beta and linear chain, all three coexist, and that will have a different type of optical activity. So this rotation from one specific rotation to the another is called as the mutal rotation. So this will be happening in all the mono and dia and all, wherever we are having a fixed carbon, anomeric carbon is available there, they will be showing mutal rotation. Let's see polysaccharide, and we'll remove this topic fast and fast because we already have covered so many things related to the polysaccharide. The number one is one of them is important, are three: starch, cellulose and glycogen. Starch is actually made up of two structures. One of them is called as amylose, which is a linear structure. Amylopactin is actually a multi-directional or like three-dimensional structure. We'll start it from starch. Just take the idea and move forward. No need to learn down anything, neither its structure as well. So we have starch is basically the main storage of polysaccharides of the plant. Starch is mainly found in plants, such as starch is found in potatoes, rice. So many things are there which contains higher amount of starch. We have cereals, roots, tubers and some of the vegetables. So in this polymer, basically alpha D glucose. Okay, learn down this. This is containing what? Alpha D glucose only. Alpha D glucose polymer. It has a C1C4 alpha cyclic linkage. C1C4 alpha glycosidic linkage, but it all depends upon C1C4 is there between the amylose, and in amylopactin it could be C1C4 also, C1C6 also. So it will be dependent on that. Amylose, it's a linear chain. As you all can see, amylose is a linear chain which has a C1C4 alpha linkage, C1C4 of alpha D glucose. But if you make the amylopactin, this will also be having C1C4, not just C1C4 glucose alpha, C1C4 glucose. अरे कौन सा साइडिक था यार? ग्लाइकोसाइडिक यार, हाँ ग्लाइकोसाइडिक, मैं उसको ग्लूकोसाइडिक बोल रहा हूँ. एनीवेज फाइन. So glycosidic linkage is there, and one more linkage is there, which is your C1 and C6 also. Glycosidic linkage is there. Because of these linkages, it exists into this form. So we have two things. One of them is amylose, another one is amylopactic. Amylose is straight chain, it's a branch chain. C1C4, it has C1C4 and C1C6. It is water soluble, it is not water soluble. It is 15 to 20% containing of the starch, and it is 80 to 85% of the starch by mass. Right? Now we have cellulose. Cellulose is made up of beta D glucose, and all the beta D glucose are having C1C4 linkages. It's a linear chain like this, cross linear chain. C1 and C4. Move forward here. No, we don't have enough time. And then we have cellulose. Some formula being given. So it's like 90% of the crystalline glucose will be given from this. Around 1000 to 1500 molecules of monomers are there in one. Basically this, and it doesn't show you mutal rotation like starch, because all the units, what we call it as the, why doesn't it show you the mutal rotation? And generally polysaccharide do not show you mutal rotation because their anomeric carbon is actually there busy in bonding. If it is freely available, then it might have shown you alpha and beta configurations, and that's how it does the mutal rotation. So it is non-reducing because there is no hemiacetal linkage, fine. It also acetylation, nitration, methylation of glucose give triacetylated solution because of the presence of 3 OH free groups, okay, fine. Then we have glycogen. Glycogen is actually found in animal cells, and glycogen found in all animal cells, occurring mainly in the liver. So it's a reserve carbohydrate for animal, and it is often used as the animal starch. Glycogen is also used called as animal starch. Okay, let us see what is it made up of. So around there are like glycogen. The molecular weight of glycogen has been, wow, that is 10 lakh from 10 lakh to 50 lakh, and contains so many structural units which are cross-linked, as shown. As you all can see, this is like C1C6 linkage. You can see C1C6. Along with that, we also have C1C4 linkages, and the monomeric unit is over here. Is what is the monomeric unit? Alpha D glucose, I guess. So which of the following polymer is stored in the liver of animal? This is animal starch we are right now talking about, is called as glycogen. This is a JEE Main 2025 question I'm showing to all of you. By this year only this question has been asked. So I would expect you people to answer me on this question. Please do it. We have sucrose, which has alpha and alpha D glucose, beta D fructose, alpha C1C2 glycosidic linkage. We have maltose. Maltose has beta D alpha D glucose and alpha D glucose, C1C4. Where can we see C1C4, alpha D, alpha D? Can we see alpha D, C1C4, alpha 1 and alpha 4? Amylopectin has 1 and 4 and 1 and 6, and lactose has beta 1 of galactose, and then we have glucose. One of them is galactose, and this is actually glucose, and glucose has a available carbonyl carbon. That's why it is also called as the reducing sugar. Correct matches: A23, B21, C24. I think A is correct only, no? B23. A is right. Let's see the another question on carbohydrate, and then from here carbohydrate will be finished. The correct statement about the following compound is or are. This is the compound actually you see. What does it have, by the way? We have OH at top, means left. This is actually beta. Beta D glucose, beta D glucose, beta D glucose. And we also see that C1C4, this is C1C4, and we have a plenty of this thing over here. No idea if it is going ahead also. Yeah, it is going ahead because this has been left empty. This means this is it's a polymer, it's a polysaccharide. So look at this, carbohydrate polymer is composed of beta D glucose, which is true. It has beta 1,4 glycosidic linkage, true. It's a non-reducing because all the C1 are engaged in glycosidic linkage. This is a true, and then all are correct. I think D is correct answer. Now we'll be having some of the tests for the carbohydrate. What tests are done for the carbohydrate? Let us look at that, and then we'll. So the test of carbohydrate, number 1 is called as Molish test. So what is the Molish test? We are not supposed to write down everything and gonna to react on the the complete chemical reaction. We don't know, but we have to just take an idea how the tests are done for what kind of particular. So just make a 1 or 2 line short notes out of it and try to figure out that where we are using this Molish test. This test is used for detection of the all types of carbohydrate, let it be mono, dia and poly. How? Because Molish reagent, which is actually 1% alcoholic solution of alpha naphthol, is once added to the aqueous solution of any carbohydrate and followed by the concentrated H2SO4, it gives a sides with a violet ring over there. the junction of these two layer, one of them which we are right now adding of alpha naphthol, and the another which beta alpha naphthol along with carbohydrate, and another layer is of concentrated H2SO4 which we are adding, will be having a violet ring between these two layers. And this violet ring actually explains us the formation of any carbohydrate can give you this test. So Molish does not distinguish between the mono, dia or poly, but yes, it can distinguish between any other component or the carbohydrate. So it will give you this carbohydrate test is there. Now I'll take you to the another Barfoed test. Barfoed test is actually done for distinguishing the monosaccharide from the other, from reducing saccharides, okay, disaccharide. So basically reducing disaccharides also give you the same test. So what we have to do is, monosaccharides are usually react in about 1 to 2 minutes, while the disaccharide take too much of the time, between 7 to 10 minutes to get hydrolyzed and then react with the reagent. So that's how a brick red color is obtained in this test due to the formation of cuprous oxide. No need to take too much of the chemical reaction out of this, but yes, take an idea of which test is being used in which time and how is it basically used to distinguish between monosaccharides and the disaccharides. Then we have Selivanov test. Selivanov test has been asked in previously few years. In 2024, I remember. I guess one of the question will come in the practice itself. So let us try this question. So this test is used to distinguish between aldose and ketose. Okay, always remember this is between the aldehydic and ketonic. We use ketonic undergo dehydration, giving a furfural derivatives which are condensed with the resorcinol to give you a red complex. So red complex is obtained in the ketonic sugars. And what has been happened in the other way? So prolonged heating with the hydrolyzed disaccharide and other monosaccharide will eventually give you this color. So I can see that ketonic sugar gives this test, okay, not aldehydic. So basically you have to remember that aldehydic sugar do not give any reaction with this, only ketonic sugar give you this test. A red color, cherry color complex is produced over there. And that's it. Now we'll take you to some questions. We have also one more test called as iodine test. So iodine forms a colored absorption complexes with the polysaccharides, such as starch gives a blue color with iodine, while glycogen gives a reddish brown complex with iodine. And it's useful, convenient and rapid test for the detection of the amylose and amylopectin and glycogen. So see, amylose react with iodine to give a deep blue or black color. Now let me see. Amylopectin gives you orange, yellow color. and from iodine and starch is actually what does it give you? Violet color. Iodine forms the violet color complex. Now try some questions, guys. Please try these questions, and then we'll announce a small break. What is the role of starch paper in making? Coloration of the ink, increase the paper. Maybe it's increases the strength. What does starch do on paper? Paper increases its strength. Which one of the following test is used for the detection of glycogen? Glycogen, iodine test is fine. Iodine test is fine. It will give you specicolor. Otherwise, Molish test and Barfoy test. Molish test will be also be given. Let me check. Only iodine test is fine, right? From other carbohydrate, let's say we have plenty of polysaccharides, then how will you identify glycogen? Using iodine test, which it will be giving a brown red color. So guys, this is something that Unacademy has brought up for all of you. If you want to enroll in our batches, so all the batches are available. You can find so many faculties are here which are right now teaching in English, also using some Hindi and English to speak up language. And there we would like to invite you all to come and join us. So just do one thing, that you got to use a code CSSR. Only use this code. So this is use code CSSR to avail these offers CSSR, and don't miss out. So right now what we are having is a small break time.